course, include then on the, I think now there some issues and shifts. Next week and the week after, that will be the logic. But before it was making basic coordinates limits.
Daar kan het worden. Je hebt wel heel weinig lijken.
More or less a side.
And the category logic is and the category logic is just a count.
Yeah.
But you can't lecture out
Okay, shall we continue? One thing that was asked during, well, a few things were asked during the break. What I'm doing now for the group of auto-preserving maps can also be done for the group of arbitrary permutations, and it's way easier there. You can just flip around a few points here and there and show that what I want here is true. The difficulty here is that you need to preserve the order all the time. And that's why when I move a point from E1, I would like to keep all the points from E2 fixed and vice versa. And that is where the difficulty lies. So, for example, in the first case where we had an A and a B, I suppose there were 10 points in between from E1 union E2, alternatingly E1, E2, E1, E2, and so on. That would mean that I would need 10 permutations in a row, first to hop over the first point, then hop over the second point, then over the third point, and so on, and they would come alternatingly from the fixed set of E1 and the fixed set of E2. So that particular A pi that I was making was a composition of 10 permutations, each one individually coming from one of the fixed sets. And so that's why I think Mostowski did it. Okay, just one point, and then by induction we jump all the other points. But what you get is an alternating product of things from the one group and the other group, vice versa. And the other thing is, why do I have all those automorphisms that I mentioned? So we can jump here and there and there, because A is isomorphic to the rationals. Every open interval of the rationals is isomorphic to the rationals. That's another theorem of Cantor's. All the countable densely ordered sets without minimum and maximum are isomorphic to the rationals. And so in the rationals themselves, they are as homogeneous as you like, because you can just add and subtract. And so once you know how to do it in the rationals, the isomorphism tells you can do it in the small intervals as well. So there's plenty of isomorphisms in the rationals to move points around with. Okay, so what do we do when the intersection of E1 and E2 is not empty? Well, suppose it is these 2 points here, E and F. For the moment, this is the whole intersection of E1 and E2. You'll get the idea. We have three intervals. Let's call them I1, I2, and I3. Here, E1 intersect E2 is empty. Because like I said, suppose this is all that is in E1 and E2, just the 2 points E and F. Here, E1 and E2 do not intersect, so use case 0, use case 1. Here, E1 and E2 don't intersect, so use case 1. So use case 1. And you can just, once you have a good permutation here, simply extend it by the identity over here. That keeps everything else fixed. So first you do your permuting here. Then you do all the permuting here, keeping the identity over here. And then the final bit of the composition is do the permuting here and leave everything here fixed. That gives you 3 sequences of permutations in a row. They're all from the group H. And their product is the one that you were looking for. Because the permutation that you want to make keeps these 2 points fixed, it means that this interval stays in its place all the time in that permutation. That permutation doesn't move anything out of E2, doesn't move anything out of E1 or E3. So you can make part of the permutation that you want here while doing nothing there for the moment. And then you build part of the permutation here, and then you build part of the permutation here. There's no problem. And so then we're done. And so why? And because I'm filling in the details of the hand waving that I did last week. Consequence and the point now is, we can show that every element has a minimum support. Why? Take one. Look at all the other supports, and there might be infinitely many, but I intersect them with my E. All those intersections are supports. Take the full intersection of that family, that's also a support, because that's a finite family, and 2 by 2 by 2 by 2 by 2 intersections will always give us supports. And so this intersection is a support, and it's the minimum. Okay, now we go to this global linear order business. we already know that the class of all pairs XE, where we leave out the smallest, all the pairs XE where E is a support of X, 4X, is symmetric. We saw that last week. And now we take a subclass of that consisting of all the pairs XE where E is the smallest support of X that is still symmetric. If you calculate the image of this, pi of X, pi of E, then because of the normality of the ideal and the way we created the filter, the pi of E is going to be a support for X, and this preserves inclusions and everything. All right. Because its symmetry group is simply the whole group. This is a okay, this is yeah. And here, do I get this? No, I'll get to that comment later. So now what? Take a member of V. We're going to associate something to it. I did that last week, but like I said, I was hand waving a bit. So we take, for every X, we take its orbit. So what's the symmetry group of the orbit? Of course. Whenever I apply something, take a member of the group, all it does is move the points in the orbit around. So, it's a member of F, it's a member of V. It's symmetric, and all its members are in V, hereditarily symmetric, and so on. And of course, this is what orbits do. They're disjoint or they are the same. what okay, I was trying to decipher my notes. So suppose we assume the global choice thing. The global choice thing gives us a map from our symmetric model to the ordinals with the following property. The map is easy. We map the orbits into the ordinals. We well order the the class of orbits, and then map it to the ordinals using the representation business, and F1 is just is the composition of that map and the G map. And we, like I said, we well order the whole family of orbits, and we get an ordinal valued map. And we compose that with the map that sends X to its orbit. So we get a mapping from V to the ordinals. This map is symmetric. If I have a pair that is in the map, that means I have an X, comma F1X, and I take its pi image, and I get this. The ordinal F1X is in the kernel, so it's invariant under pi. Oh, wait a minute. Yes, but pi x and x have the same G, therefore they have the same F1. So if I start with a pair in the function, I apply any permutation to it, I get another element in the function. So this class is symmetric. Oh, here it is. But of course, this map is not injective because it's constant on the orbits. We have another map. We already saw it. Okay, I erased it, I think, just now. This is simply the pairs x comma e, where e was the minimum support of x. That is a function. That function is symmetric. And so is this. The map that sends x to first the ordinal that goes with its orbit, comma, its minimum support. That's also a symmetric function, symmetric class. Because if you do the permutation of the triples, so to speak, then you simply get the permutations of all the coordinates, and we have seen that that works out the way it should. Okay, so we go. So this maps into the ordinals cross the ideal, and we can order the finite sets in A, we can order them lexicographically. How? Well, look at their characteristic functions. How many points are there where these two functions are distinct? Well, outside the union of E and F, both functions are 0. That means there can only be finitely many points where they are different. We have a linear order on A, and here is where the linear order on A becomes important. So we have a first member of the points where they differ. And then we check whether the value of the characteristic function at A, the minimum, is 0 or 1, and the 0 comes first and the 1 comes later. So we can linearly order the finite sets using the lexicographic order induced by the linear order that we got from A. Oh, done. We order V lexicographically. First, we look at the ordinal. If that helps us decide, then we're done. Then we look at I. Oh, wait a minute, I forgot something. I almost forgot. The map is injective. Suppose we have two things with the same image. Well, it means Because f1 of x and f1 of y are the same, it means that x and y are in the same orbit. So y is pi of x for some pi. And what do we get when we calculate the support of x? Sorry, the minimum support of x is E, then the minimum support of y is pi of E. And here is where we need that one fact about the supports and their symmetry groups. Pi of E is equal to E, so pi is in the symmetry group of E. But the symmetry group of E was the same as the fixed group of E. So pi of x is equal to x, because E was the support of x. So all the way to the very last moment, this is what saves the day, that for the members of I, the symmetry groups and the fixed groups are the same thing. That will help us get an injective map. And now I go back to here, order lexicographically, look at the first coordinate, ordinal. If ordinal for x is less than the ordinal for y, fine. If they have the same ordinal, they have the same orbit, then the ordering of the supports will tell you which comes first. Because that's a linear order. So we do get only, apparently, a linear order, global. Now, there was a question again during the break. Okay, proper class, scary things. What does it mean? Well, a proper class is symmetric if it's invariant under the permutations. Just like a set. You calculate the images of the members and see if they still satisfy the class thing. You could also formulate it as a formula. You can take the whole proof and write out the ordering that we get here in terms of that, in terms of the f, in terms of, oh, okay, now I have a formula that whenever I permute the variables, I get the same thing again. That means I get a symmetric formula that linearly orders the whole class V. Whenever I stick two elements in it, I can decide which comes first, which comes later. So you can translate it back to the formula language. If you don't like proper classes as individuals, fine. If you don't even like that, replace V by a member of itself. That member is invariant under lots of permutations. And you can simply relativize the whole affair to the members of your set. Take their orbits inside X. Take their supports and don't look any further, and then this will give you a linear order of that set. Don't say, I'm looking at all the members of V, just looking at all the members of... If you could say, well, take a level in that cumulative hierarchy, take the power set of the power set of the power set, power set a few times. That set, I can give a linear order, and it linearly orders every member that's in there. But the point is, this formula, this method of ordering is completely uniform. It applies to every X at the same time. So if I have if my ingredient is a global well order, the result is a global linear order. If my ingredient each time is a well order for X, or something related to X, then we get a linear order for X again. The formula that translates the well orders into the linear orders is completely uniform. It's just the one thing. And that's why we get the global result as well. So I think I said about that what I wanted to say. Okay, so how much time do we have? Okay. So now, one of the questions, even I think the 2 weeks ago already was, yes, okay, fine. Are these atoms consistent? How the hell do you build a model for atoms when we don't have any atoms in our universe? If we're starting with, say, the axiom of regularity and everything, then there is no set that doesn't have any members unless it's the empty set. Well, this also has something to do with the other question that I got. What about the axiom of regularity, and what about set theory without atoms? There are two things that you can do. Atoms, what atoms? So assume we have Z of C in our universe. So we have the axiom of regularity in our universe. So our universe is built up using the iterated power set business, starting only with the empty set and everything. How do we create atoms? Well, here is the universe. V. This is not the V with the atoms, but never mind for now. And so we build up, and here somewhere is here is V omega. Well, that's all the finite sets, all the hereditarily finite sets and everything. And then we get the next level. And that suddenly contains all these subsets of omega, all the subsets of this thing. That's suddenly cardinality continuum. Take an infinite family of infinite subsets of omega. So here they are. And now what? Well, okay, the details are a little bit, you need to work a little bit on the details on paper, but this is what you do. You start building you take these points and you start building the power set from here. So you take this, you take its power set, you take a power set, you take a power set, power set, power set, power set, but this is going to be the bottom level of your universe. And one of those will simply be the designated interpretation of the empty set. Remember, we had two constants in our ZFA language. The empty set was an explicit constant, and A was an explicit constant. Well, the empty set needs an interpretation, and it's going to be just one of these points over here. We're simply saying you're going to behave like the empty set. And the constant A will be interpreted by that family. Now, why does this work? Well, there is nothing in this universe that is a member of any one of these things. We very carefully excluded all the normal natural numbers and everything, because we only look at those points and everything above it. What can you say about, why did I take those infinite sets? Because I didn't want to run the risk of one Cn being a member of another Cn. You could have said, well, why didn't you take the infinite subset here somewhere? Yeah, but before you know it, one is a member of the other. Suppose I had taken the natural numbers. Well, yeah, those are ordered, and 5 is an element of 10 and everything. I want things that definitely never are going to interfere. So I can make these guys disjoint, so they are really, really separate. And those are the initial points of my universe. I simply build up the power sets and everything in there. And this, okay, it takes a bit of scratch paper, but this satisfies all the axioms that I talked about 2 weeks ago. Why? Because you interpret everything faithfully in that class. So how do I know the pairing works? Well, of course, if I take one or two of these guys, the set that consists of these two things is in the next level. Every subset of this is in the next level. And if I want to build relations and everything, they'll be there. If I'm taking a union of some family, it appears 1 or 2 levels up. If I take a power set of some family up there, it'll appear a few levels up. If I want to prove the replacement axiom, it means I have a function from here to there, and I have a member of that set, and I want to show that the image is still here. Yeah, well, all the members are up here. The set is a member of that universe, so there. That's the whole nice thing. We assume this whole universe satisfies replacement and separation and choice and whatever it is that we wanted to satisfy. And whatever we do, when we check an axiom, always we know that the results is in the universe V. All we need to do is check that it is in that partial universe up there. And that is almost automatic. Choice, if I have a set up here, it has a well order, V tells us, but that well order is a set of ordered pairs. They're higher up in the hierarchy. So they're in this universe up there. This partial universe satisfies all the axioms that we want.
Are the axioms of ZFC or ZF?
ZFA.
Yes.
So this if we assume choice, we get choice. If we don't assume choice, we don't get choice necessarily. So you can say, I don't believe in choice, I only believe in ZF, well, you get ZFA here. If you do believe in choice, you get ZFA plus choice here. And we did ZFA plus choice because we needed some well orders in advance and then maybe show that they were symmetric and everything. So that's very briefly how you could make this work. What if you don't like atoms? Well, have a look at the homework. There is another trick which I stole from Koonen's book. That's this. You can take, I'll briefly sketch what you can expect. You can take a bijection, a class bijection, whatever, of the universe, and you can define a relation on the universe by saying x is in relation to y. It means that x is a member of f of y. Now, so f is basically an extra formula that connects pairs. And here the interpretation of the directed graphs and everything comes in nicely. This defines a directed graph. There goes an arrow from x to y if originally x was a member of f of y. So you get the directed graphs that Benedict Levertol talked about in the beginning. And you can ask, does this directed graph model satisfy the axioms of Z of C or ZF? Yes. You can check pairing, union, power set, separation, replacement, choice, if you want to, except for one. Yes. I didn't mention, oh, extensionality, you get that? So what was it that I didn't mention yet? Regularity. Suppose we use the cycle notation and we let f be just one flip, one transposal. It transposes the empty set and 1. All the other points in the universe stay in their place. In that model, in that directed graph model, you have an X that is its own singleton set. The empty set is its own singleton set in that particular model because the empty set is a member of F of the empty set. So that directed graph model doesn't satisfy regularity because this contradicts regularity. Regularity says you cannot have one of those x's, for example. And and this one is on the homework. Suppose you take an f that flips n and singleton n for every natural number. Then you get an infinite set of things like this. Because in this structure, every natural number is its own singleton set. It is no longer the natural number of the new structure. The new structure has other animals that behave like the natural numbers. That's the whole point here. But this structure contains a copy of the original one. So the well-founded sets of the new structure is just the old universe. And the points that satisfy this property, they behave just like the atoms in the ZFA models. You can do permutations of those. There is nothing new happening. It's complete parallel. We had atoms, kernel. Now we have points that are their own singleton sets and something that arises from the empty set. So we can say this structure proves the consistency of ZF minus regularity plus there is an infinite set of things that like that. Start with a model like that, do the power set thingamabob, and you have another permutation model, way of creating permutation models. So one or two of those things I put on the homework, so you can have a look there. And most of the time, when you need to show the existence of something, it's usually F inverse of the thing that you normally expect. Or F of the thing you normally expect. Sometimes you go back, sometimes you go forward. So it's, again, you use that the normal universe satisfies all the axioms, and then you say, oh, but I have a bijection, so the thing that I need, I can make using that bijection. Okay, have fun with that. I yield the floor.